Let's get started on this example. Here we have a heat pump cycle using R134A as the working fluid. The cycle consists of a compressor, which then goes into a condenser where some heat is released to the hot reservoir. And then it goes through an expansion valve into an evaporator. The evaporator is where heat is coming in from the cold reservoir, and then goes back into the compressor. There obviously has to be some work that goes into the compressor in order to keep the cycle working. We're given some information about states. That's shown on the right-hand side here. We're asked to determine the coefficient of performance for this heat pump. So we'll do that first. And then the next question is, if the valve were replaced by a turbine, so if we replace this expansion valve with a turbine where we could produce some power, we could actually reduce the power requirements of the heat pump. We would make the heat pump coefficient of performance even better. And we want to know is, would we recommend this power saving measure? And we need to explain that. So basically, part B is replace the expansion valve with a turbine and then see what our coefficient of performance is for that particular situation and whether that is enough to make it worthwhile to make the recommendation of replacing the valve. All right, so let's start with part A first. Let's determine the coefficient of performance for this heat pump. So in order to do that, let me first of all just remind you, I said this in words, but we'll just go ahead and show it. The condenser, or the evaporator, is where the heat is coming in. So we've got a Q dot in down here. That's heat coming in from the cold reservoir. And then that would be like our surroundings for the heat pump. And then in the condenser, that's where the heat is being released. So I'm going to draw it as Q dot out. And that's going into our hot reservoir. So if I drew the corresponding kind of high level picture here, we've got our system. Here's our hot reservoir, our cold reservoir. Here's where the power is coming in, W dot in. And this would be our Q dot H and our Q dot cold. The dashed line here, that's our system. That corresponds to the same dashed line that I'll just draw right here. So you can see that our system consists of that compressor, condenser, expansion valve, and evaporator. The Q dot in is our Q dot C. I'll just make a note of that over here. And our Q dot H is our Q dot out in our picture. So we want to find the coefficient of performance for this heat pump. So let's just write that down. The coefficient of performance for a heat pump. What we care about there is we want to get as much heat into our hot reservoir. This would be like a house, for example. We want to get as much energy into our house as possible while minimizing the amount of work or power we have to put into the cycle in order to make that happen. So this will be Q dot H over W dot in, or since I called it Q dot out, I'll just write it as Q dot out over W dot in. And this is over the cycle. So in order to figure out that coefficient of performance, we need to know the power coming in. Well, that's already given. That's at the 5.17 kilowatts. So all we really need to do is find the Q dot out, which would be focusing on the condenser. So let's draw a control volume around that condenser. And then we need to find the heat transfer there, we'll apply the first law. So let's write out the first law for the condenser. So we need to write out the basic equation. Again, always start with the full basic equation, and then we'll use our assumptions to simplify this basic equation. Okay, so let's go ahead and simplify. We're going to assume steady state operation. So the time rate of change of total energy in the control volume is 0. We'll assume that the device is a passive device, so there is no power to worry about. And oh, actually, I'm going to modify the form of this first law. Since in the picture I used a q dot out, I'm going to go ahead and change my first law expression. Instead of being q dot plus q dot in, what I'm going to do is write it as minus q dot out there, just to be consistent with my picture. So the q dot out is what we're trying to find. All right, getting back to the other terms, the kinetic and potential energy terms, we're going to neglect. We're going to assume those are small, which is a very reasonable assumption. And then the other thing that we'll do, I'll put this off to the side, is if we applied conservation of mass to that same control volume, I'll just write that down over here. What you'll find is, again, because it's steady state, the left-hand side goes to 0, and you'll get m dot in is equal to m dot out, which is just m dot for convenience. So when we simplify and rearrange our first law, we'll get q dot out is equal to m dot times, this will be h in, which in this case would be h3, minus h out, which in this case would be, oops, I'm sorry, I messed that up. The inlet part is h2, and the outlet is h3. So that's our expression for q dot out. And we could, so we then can try to, what we need to do is we need to find the specific enthalpies at these various states. So this is where the states are going to come into play. So at state 2, we're in pretty good shape. We know what, we'll be able to find the specific enthalpy from that because we're given 2 properties. Problem is at state 3, we're not given enough information. So we're going to have to resort to something else to find another point on at state 3. All right, so we're going to have to try to find that state 3 condition. I'm just looking at this for a moment. I think there's one piece of information that was missing in this picture. Actually, I'm just looking at my notes here. It turns out, yes, we are in fact missing. Right up here at state 3, we're told that this is saturated liquid. So that should have been added. Let me highlight that. That's a given at that point. I evidently didn't type it in. So we're given that it's a saturated liquid at state 3. So that actually should be in the problem statement. So that's actually our other piece of information that we need to figure out what's happening there at state 3. All right, so let's write down our properties. These are coming from the R134A tables. So again, at state 2, we know that P2 is 9 bar, T2 is 60 degrees C. So if you go to the tables, what you'll find that corresponds to superheated vapor phase, with H2 being 295.13 kilojoules per kilogram. And then state 3, we know that the pressure there is 9 bar. Also, that makes sense because as you go through the condenser, we assume the pressure remains constant. But we're also told that it's a saturated liquid at state 3. So we can go to our tables. We know it's a saturated liquid. We know the pressure, so we can easily look up what H3 is. It comes out to be 101.64 kilojoules per kilogram. And then the last little piece of information that we need to solve for Q dot out is the mass flow rate. So we now know H2, we know H3, we need the mass flow rate. Well, the mass flow rate is that we're going to have to be able to find. We're given it in state 1 here. We're told that the mass flow rate is 7 kilograms per minute. So we should convert that over. So m dot is 7 kilograms per minute. Let's put it in, we'd want to convert that over to kilograms per second to help us with our units. So That'd be 7 kilograms per minute. And 1 minute is 60 seconds. So that'd be 7 over 60 kilograms per second. I didn't work that number out specifically, so I'll just leave it as 7 over 60. So we can plug those numbers into the expression we have for Q dot out. And what we'll get when all is said and done is this comes out to be 22.574 kilowatts. We now have our Q dot out. We know the W dot in, that was given in the problem statement here. It's 5.17 kilowatts. So then we can determine the coefficient of performance using the expression we have up here. So let's do that. Coefficient of performance for our heat pump cycle, again, will be Q dot out. I'm just repeating it here over W dot in. And when you plug in the numbers, it comes out to be 4.37. All right, so that's part A of this problem. Let me go back up to the problem statement. So we've done the coefficient of performance for the heat pump. Now what we want to do is replace the valve with a turbine. So the idea here is we're going to eliminate this valve, and then instead we're going to put a turbine here. So it looks something like, I'll tell you what, I'm going to draw it back down here. I'll just redraw the system. So we've got a condenser here, Q dot out. What we're going to do is we're going to have a turbine here. There's going to be some W dot out from that turbine. This is our state 3 here. This is state 2. Here we have our compressor over on the right-hand side, just as before, with our W dot in. That'll stay at 5.17 kilowatts. That's given in the problem statement. And then we have our evaporator down here. That's where the heat is coming in from the surroundings. Okay, so this will be our new system, our new cycle that we're going to investigate, because we're replacing the turbine. We're replacing the expansion valve with the turbine. And the reason we're considering this is because we can generate some power out of the turbine, that might help reduce the net amount of work that we have to put in. So we take some of that power and just put it right back into the compressor, and so that would make our whole cycle a little more efficient, right? So our coefficient of performance in this case, let me just draw the control volume corresponding to that. This would be our, oops, I should have drawn that a little better. Let me try again. So our control volume is going to look like this for calculating the coefficient of performance. And if I draw that picture over again on this side, it's our hot reservoir up here, cold reservoir down here. There's our Q dot in, Q dot out. What we're going to have now over here, we'll call it W dot in net, which will be our W dot in that we started with, the 5.17 kilowatts, minus the W dot out, which we're going to calculate for the turbine here in just a moment. And our coefficient of performance for this heat pump, and I'll put a little prime on it to indicate that it's different from the first one, will be our Q dot out all over W dot in net. Right? So the real difference here is that we're dealing with the net quantity now for our primed coefficient of performance. So we need to determine the work or the power coming out of the turbine. The power going into the compressor, it's going to be the same. We're going to keep it the same. We still have the same Q dot out. Let me just set a reminder here. Q dot out we just solved for, that was 22.574 kilowatts. So that'll stay the same. We're just really focused on the W dot out. All right, so in order to find W dot out, what we're going to do is apply a control volume around the turbine. So we'll just draw that control volume there. And we'll apply the first law to that control volume. Okay, so first law to the turbine. So let's write it all out. Hopefully you have this equation memorized, the first law. You've used it many, many times. And so to simplify it, so we know the first term is 0 because it's steady state. We're neglecting kinetic and potential energy changes, so those are gone. We'll assume that the turbine is adiabatic, so that's 0. And again, from conservation of mass, m dot in equals m dot out, so we'll get W dot out is equal to m dot. So coming in is state 3, going out is state 4. Now, the state 3 specific enthalpy we already know, right? We found that up here, so let's just for convenience write it down. It's 101.64. It's right up here. 101.64, so let's write that down. But we still need to calculate what the H4 is now. So in order to find that H4, we need to say something about this turbine. What I'm going to do is say that if we're going to put a turbine in here, let me consider the best case scenario. Let's replace the expansion valve with a turbine that is working under ideal conditions, like the most efficient turbine that we can possibly have. Because what we're trying to do here is evaluate, under the best circumstances, is it worthwhile to replace the expansion valve with a turbine? So I want to consider a turbine that's operating under ideal conditions, where it's operating in its most efficient way. So in order to do that, what I'm going to assume is that the turbine operates in an internally reversible manner. Okay, so let's jot that down. So assume the turbine operates in an internally reversible manner. And again, the reason I'm doing that is I want to see, even in the best case scenario, is it worthwhile to replace the expansion valve with the turbine? And the best case scenario would be where there's no inefficiency, where there are no irreversibilities within the turbine. So I'm going to assume that it's an internally reversible manner. Okay? Since our turbine is also adiabatic, so turbine is also adiabatic, it's well insulated, so the process is adiabatic. We assume that right up here, just our Q dot was 0. Since it's internally reversible and adiabatic, that means that it's operating isentropically. So that means that we're going to, under the ideal scenario here, we're going to assume that our turbine is operating isentropically, which then means that S3, means that S4 is equal to S3, right? So and actually, you know what I'm going to do? I'm going to give it a different name. I'm going to call it 4S, because up here we had state 4 right there, but now state 4 is going to be a little different than it was. When we had the expansion valve, state 4 is a little different than if we have the turbine here. Okay, so just to differentiate between the two, I'm going to call, up here it's still state 4 when you have the expansion valve, but now that we have the turbine, I'm going to call it state 4S. The S just indicates that I'm assuming that we're dealing with an isentropic process from 3 to 4. So that's why I'm putting the S in there. So just to show that we're dealing with a different state 4 because I'm assuming isentropic operation of the turbine. So in my previous expressions up here, I'll replace 4 with 4s. So I've just replaced it right here with a 4s. Okay? And then I'll assume the specific entropy at 4s is equal to the specific entropy at state 3 because we're assuming isentropic operation. So that means I need to find the specific entropy for state 3. We can do that using the property tables. We know again that at state 3, we know the pressure, we know that it's a saturated liquid, so we can look up the specific entropy for that. So let's do that. So state 3, again, the pressure at 3 was 9 bar. It's a saturated liquid. So we can use the R134A property tables, and that comes out to be 0.37387 kilojoules per kilogram Kelvin. So now we know that at state 4s actually, we now know that S4s is the same as what it is at state 3, so it's 0.37387 kilojoules per kilogram Kelvin. And then the other thing that we know about state 4s is that the pressure is still the pressure at state 4s will still be 2.4 bars. And the reason I know that is through an evaporator, the pressure remains constant. So if the pressure at state 1 is 2.4 bar, then the pressure at 4 has to also be 2.4 bar. So that's our other piece of information, is that the pressure at 4s is also 2.4 bar. So now we have two properties. We can go back to the property tables for S134A, or I'm sorry, the refrigerant 134A. And what you'll find is that this puts us in the saturated liquid vapor mixture phase. And so then we have to, so we'll have to calculate a quality here. So to find the quality, we'll find the saturated liquid value for the, let me write this differently, the saturated liquid value for this specific entropy. That comes out to be 0.17803 kilojoules per kilogram Kelvin. The saturated vapor value is 0.93465 kilojoules per kilogram Kelvin. Again, you can see that our value for the specific entropy falls in between those two, so that's why we know it's a saturated liquid vapor mixture. So you can find the quality at that point. Looks like this. So we can plug in our numbers, and you'll get that the quality comes out to be about 26%. It's 0.258845. And then once we have our quality, we can find our specific enthalpy at state 4s from the quality. And so there's some property lookups that you have to do here. Calculating these properties is not particularly hard. It's just very tedious, and it's easy to make mistakes. So you just have to be extra careful looking up the values and then writing them down. And you know, I use a spreadsheet typically when I solve these kinds of problems. I know that you don't have that for an exam, but at least for homework you do. So anyway, when you plug in these values, the specific enthalpy for 4s comes out to be 97.12966 kilojoules per kilogram. So now we have our two specific enthalpies. We have H4s And then we also have the H3 from before. We can plug those into our power along with the mass flow rate, the 7 kilograms per minute. And what we'll get out of the turbine then comes out to be 0.526 kilowatts. It's a pretty small number. Remember that the power that goes in, if we go back up here for a moment, the power that went in was 5.17 kilowatts. So what we're saying is out of this, if we replace the expansion valve with this turbine, we're only getting about 10%. We're saving about 10% of the power. Anyway, we can make use of this to calculate our coefficient of performance for our modified heat pump cycle. And when you plug those numbers in, it comes out to be 4.86. So it's, oops, I did a terrible job there. 4.86. So again, just let's compare that to our original heat pump cycle. It was 4.37. Let me just make a note of that here. So the original one was 4.37. So we've improved the efficiency to some degree. Not a whole lot. In fact, if you look at the percentage increase, that'll just be the COP for the modified heat pump cycle minus the COP for the original divided by the original. That comes out to be about, I believe it comes out to be about 11%. So we've improved the efficiency of our heat pump cycle by about 11%. So that's an improvement. That's great. You know, we always like improvements. It's not a lot. And you got to keep in mind that this is for the best case scenario. That turbine is operating in an internally reversible manner. There are no inefficiencies in that turbine. So at the best possible scenario, you're getting an 11% improvement. Under more realistic conditions where you have some irreversibilities, it's going to be less than that. So, you know, at best it's 11%. Now think about this. We're going to add in a turbine, which means that it's going to cost more than an expansion valve. Is pretty cheap. It's a piece of equipment. It just doesn't move. It's a very simple static piece of equipment. A turbine has moving parts. It's going to be expensive. There's more complexity of integrating it into the system. It's adding additional cost. So you have a cost and complexity that are going up for at best an 11% improvement, probably more realistically something closer to, you know, 8 or 9% improvement. The other thing that is a factor is, and I've talked about this before in lecture, but turbines typically operate where the quality is close to a value of 1, maybe even in the superheated vapor region as well. And the reason for that is as material moves through that turbine, we don't like to have a lot of droplets of a liquid in there because those droplets impact the high-speed moving turbine blades, and that causes some wear and damage on the turbine blades. So generally you want a turbine to operate at a high quality or even in the superheated vapor region so you don't have those liquid droplets. But if you look at what our quality is, we're starting from a saturated liquid at the entrance of the turbine, and then the quality as it leaves is about 26%. So we have a lot of liquid in this turbine. It's really kind of a messy situation here. You've got some gas, a lot of liquid. It'll just cause a lot of wear and tear on the turbine. So it'll make it challenging to actually operate effectively and without a lot of damage. So when you factor all these things in together, you know, a relatively small increase in performance, but it'll increase the cost and complexity quite a bit, and the turbine will probably wear down pretty quickly because of the presence of all that liquid. In the end, I wouldn't recommend incorporating a turbine. So that's really the answer to part B here is, would you recommend this power saving measure? And the answer is no, not really, because other factors become important and you just don't get that much of a benefit from, you know, an increase in thermal efficiency. That's in fact why these heat pump cycles and refrigeration cycles use expansion valves rather than a turbine because you just don't get much out of the turbines. So you might as well go with something much simpler and save on other parts of your engineering consideration like cost, complexity, etc. Longevity. All right, we'll go ahead and end right there on that example.